Hiya. This is a bit of a different video compared to what I usually do. So what I'm going to do here, I'm going to Paris on Sunday. Today is Saturday, so tomorrow. And on the Thursday there, I have a presentation I need to give. So this is a physics video, so to speak. I'm going to run through my presentation basically, because I figured it's nice to have it somewhere before, well, okay, anyway. The thing about this presentation is it's at the EIC Electron Ion Collider Users Group meeting, so it's assumed everyone knows a bit about the Electron Ion Collider. So I'm going to explain that briefly before I start the presentation. So the Electron Ion Collider is a big accelerator that will be built in the US in the near future, sort of, hopefully. So we expect around 2030, which is in these terms the near future. And what it's going to do is collide electrons with ions to probe the inside of the nuclei, basically. So this is very much like, if you remember Rutherford's gold foil experiment, where he fired electrons at a gold foil and see how they bounced back. This is a lot like that, but with higher energies, and higher energies means we can probe deeper, so we can actually get into the nuclei rather than just seeing that there are nuclei. So that's the whole point. And then the whole technology is a bit more advanced, of course. So I'm working on the innermost detector of that, basically. So let's get to the presentation, which sort of deals with all these things, yeah? Apparently it's going to be 40 degrees in Paris on Thursday when I'm giving my presentation, and I got an email saying there's no air conditioning. So we'll see how that goes. Anyway, let's get to this, shall we? Everything looking good in OBS? Yes? Good. So, I'll do this as the proper presentation. So, hello, I'm Håkan Menlöv. I'm from the University of Birmingham, where we work on studies of the silicon Vertex tracker for a future electron ion collider. So I'm going to be talking about that. That's a silly thing to say, sorry. This is an outline of my talk. I'll start talking about the silicon Vertex tracker, why it's important, what it is, why we need it. Then I'll move on to talk a bit about the simulations we do for it, which are used to determine the geometric parameters of the silicon Vertex tracker, such as the positioning of the sensors, the extent of the layers, and the pixel size, and so on. And then I'll go into a bit more detail about the pixel sensors, which are the parts that make up the silicon Vertex tracker, because this is the main part of the work carried out this last 6 months anyway. We're also working with the Rutherford Appleton laboratory in England towards constructing an EIC specific sensor. So I'll touch on that briefly, and then the conclusions of the talk and future outlook. So first of all, the silicon Vertex tracker. It's the innermost part of a detector. So what you see here in these images are at the top, I can point with this, a concept for BNL, Brookhaven National Lab, and at the bottom a concept for JLab, so there are two possible locations for this project. Now the part I work on is in the very center here, so it's really the detector closest to the interaction point. And this, the layout of this, how it works and such, won't change much depending on the location, which is quite nice. It's a bit independent until we have CD1. This is the main detector for vertex position finding, which is important for tagging different particles. So, for example, in the collision between the electron and the ion, these zero particles can be created, and these decay within 120 micrometers from their creation. So that's still within the beam pipe. But if we have very fine spatial resolution, we can still separate the primary and secondary vertices. The detector also contributes to momentum measurements. So what we need is very fine spatial resolution and also low material, that is in terms of radiation length, so we reduce the effect of multiple scattering. Now, one thing we do is simulations. So we study a full silicon Vertex tracker using EIC root, which is a specific simulation package developed for the EIC. It contains a particle generator, geon propagation through the detector, hit digitization, and track finding. So here you see some images from the simulations. This blue thing is the TPC, which is outside the silicon vertex tracker, and all the yellow and green is the silicon vertex tracker. And here is a zoomed in view, and you can see different layers at different distances away from the beam pipe. The figures of merit, the parameters of interest we look at, are the momentum resolution and the pointing resolution so far. Pointing resolution in both longitudinal and transverse directions, but these follow the same trend, so I'll only present the transversal here. So we studied different layouts and different pixel sizes. And also we've tried adding a separate outer layer that's a bit thicker that could be used for timestamping to see how that affects the resolutions. And we also made at more forward rapidities studies inserting disks into this. So here are some simulation results. This shows having a silicon vertex tracker versus not having it at all, which is the only TPC curve, the magenta one. So on the left plot is relative momentum resolution, and the right one is transverse pointing resolution. And we see here that, well, only at very low momentum, it's better to not have the silicon vertex tracker, and this is due to the material it adds, causing multiple scattering, which is more important at low momenta. And for the transverse pointing resolution, it's just everywhere much better to have a silicon vertex tracker than to not have it. You see, we get the pointing resolution down to under 100 micrometers rather than 300 as we get with the TPC. These studies are made with positive pions in pseudo-rapidities between -0.5 and 0.5, so it's very sort of narrow, just up the barrel, so to speak, orthogonal to the beam pipe. These results are for different pixel sizes. Again, the relative momentum resolution on the left and the transverse pointing resolution on the right. And we can see that pixel size has no effect on the momentum resolution at these, well, in this configuration. We also see that the pointing resolution improves with reduced pixel size. Now, this is of course expected from the theory, but it's nice to see it pop up in the simulations as well. Smaller pixels are better, so we want pixel sensors, and this will lead on to the rest of the talk. So for best performance, we want to use small pixels located near the interaction points. So moving on to pixel sensors, there are basically two different kinds of pixel sensors. There are hybrids and monolithics. Now in hybrids, the sensitive volume and the readout electronics are on separate chips, and then they are bump bonded together in general. There are some other methods as well. So up until now, this is the most commonly used pixel sensor in silicon vertex tracker. However, quite recent developments have been introducing monolithic active pixel sensors, in which the sensitive volume and the readout electronics are on the same chip, hence the name monolithic. And they are made using commercial CMOS technology, which has some benefits. There are also a special case of this, depleted monolithic active pixel sensors, DMAPs, which are utilizing high voltage, high resistivity CMOS technology. And the depleted means that the depleted volume is intended to be as large as possible, and this helps the signal. So the advantages of DMAPs are, compared to hybrids, they have lower cost. It's possible to mass produce them in commercial CMOS technologies, and this is, again, cheap. It's also easy to manufacture loads of it, and we will end up needing a few square meters at least in the full detector. They also have a lower material budget than hybrids, which again reduces multiple scattering. We avoid bump bonding, which is complex and laborious, which is good. And the depletion gives faster and more uniform charge collection, which is very good for the sensor part of it. So in Birmingham, we studied some test chips. They are called the Tower Jazz Investigator chips. They were originally developed for the Alice in a tracker upgrade investigations. So it's a monolithic test chip, which has many different pixel flavors on it on the same chip. So different pixel sizes, different collection electrode sizes, and different spacings between collection electrode and POL, which contains the electronics. So we have two process versions called the standard and the modified process. You can see them down here. So this is the standard process. This is what is used in the Alice in the tracker upgrade. It's called the Alpide chip, which is also our baseline. We'll come back to that. What you see here is the depletion grows from the collection electrode. So the depleted region is all right. It's not huge. So here, charges are collected by diffusion outside the depleted region, and then inside they're collected by drift. Here is the modified process, which introduces a deep planar junction here, which the depletion grows from. And here we reach full depletion even under the P-wells, and charge is collected by drift everywhere. Some measurements have been done with these chips using an iron 55 source. Now, the overall goal of this is to have a small collection electrode, which gives a low capacitance. And this means we can have smaller pixels with lower noise and lower power, and the depletion again increases the charge collection. So, here are some results from the studies. This is comparing the standard and the modified process. Again, iron 55, what you see on the left here is the amplitude spectrum. So you see the two peaks, the K alpha and K beta for the two different ones. And immediately we see that the modified process has a higher signal to noise ratio than the standard process. Looking at the rise times, which is this, the right-hand plot, we see that the modified process in red has shorter rise time, so charge is collected faster, and it's also narrower, which means that there's a more uniform charge collection mechanism. So this again indicates a fuller depletion. Now, for a 20 by 20 micrometer, this is results for a 28 by 28 micrometer, which is the same as our baseline, the LP'd. For a 20 by 20 micrometer pixel, the differences are smaller, and this is due, at least in part, to that the percentual depletion will be larger already in the standard process, because, well, the pixel is smaller, but the depletion region has sort of the same size. And for larger pixels and spacing, we've noticed that the modified process actually shows worse performance than the standard process. We think this is due to the P-well coverage. We'll get back to this in a bit. We also have a chip that allows separate biasing between the P-well and the substrate voltage. This is called the TauJazz 1B. And here are results from that. Again, we have the amplitudes of the RM55 on the left and the rise times on the right. So what we can see is that increasing the high voltage, keeping the P-well the same, the signal to noise ratio decreases. Now this is a bit unexpected. Naively, you'd think that the charge gets collected better if you have a higher voltage, but that's not really the case here. We also see that, looking at the rise times, the distributions get wider when we increase the high voltage, and actually at -15 they sort of go to a double peak structure. So this is unexpected and interesting. We can see that this double peak structure comes from smaller charges being collected slower, and these charges come from the pixel edges. So the conclusions from this part of the study is that the modified process performs better up to a 30 by 30 micrometer pixel size. At smaller pixels, there's a smaller difference, potentially due to the percentual P-well coverage, but also the relative size of the depletion region, so to speak. And we've seen that higher bias voltage does not improve the signal, and this is due to the shape of the electric field. So our results are consistent with simulations and published results for a similar sensor. And here you can see simulation, a TCAT simulation of the pixel done by Magdalena Munker of Click. So here is the P-well, and here are two collection electrodes. The colors are the electrostatic potential, and the electric field lines are drawn. What we have here at the star is a minimum in the electric field. So what happens is that charges that hit between the pixels, like here, they get pushed to the electric field minimum, and then they quite slowly drift toward the collection electrodes. And this effect worsens when we increase the high voltage. So higher potential difference between the P-well and the substrates gives a longer path and a slower charge collection. So how do we fix this? Well, there have been some suggestions, and they have been implemented in silicon in what's called the Mini Malta chip. So there are two modifications suggested, well, implemented even. So the first is an extra deep P-well, which sits on top of the normal P-well here, and the other is a gap in the N layer here. And both these modifications have the purpose of sort of funneling the electric field towards the collection electrode to remove the badness at the corners. Now, analysis is ongoing of test beams of this chip. Initial results are positive, but there's a publication in the work, or several even, so I can't present the results here. This pixel size is 36 by 36 micrometers, so it's larger than what we want, but it's still interesting to learn more about the technology. So, with the Rutherford Appleton laboratory, we are using these results, among other things, to work towards developing an EIC specific sensor. So, the goals here are mainly, of course, to develop a high granularity silicon vertex tracker, but also to investigate the feasibility of having a separate timestamping layer to keep track of the bunch crossing and thus the polarizations of the beams in the collider. The challenges mainly are the timing and the pixel size. So here on the right you can see a table of some of our requirements. Marked in red are the most stringent ones. So we want a small pixel size. If we have a separate timing layer, we want it to be larger. This isn't super large, this is still micrometers, 350 micrometers. This comes from the resolution of the time projection chamber. The timing resolution will depend on the site. So if it's at BNL, we need 9 nanoseconds, and if it's at JLab, we need 1 nanosecond. We also need to keep the power down to keep the material down with the cooling and such. So the latest results we have, the power, noise, and fake hit rate is based on the Alice ITS specification. So again, the LP is our baseline. So the latest results is that we can reach a timing resolution of 4 nanoseconds, which is very fast, using a constant fraction discriminator. However, a CFD draws a lot of power, so we can't fit this in a small pixel. But this study is continuously ongoing. They're working at it at RAL, and we have meetings once a month. So this is exciting. And this leads on to the conclusions and outlook of this talk. So the conclusions are, the simulations show that we want a small pixel size and detector layers as close as geometrically possible to the beam pipe. The tau adjust modified process already suits our needs, but the sensor layout is crucial. Again, with this electric field minimum, we need to be very careful about that. So these extra modifications can be potentially beneficial to us, but it needs further investigations for the pixel sizes we want. And this is where we're at now. So in the future work, first of all, we'll continue the sensor development with RAL. For the simulations, we intend to start full event reconstruction simulations, actually sticking proper physics events in and then propagating them through the detector, reconstructing mass and such, investigating the actual heavy flavor observables. We will also test single photon avalanche diodes, SPADs, because they're very fast sensors and they have a fine granularity, but allegedly they're not very radiation hard. But since the EIC is relatively low radiation compared to other collider experiments, we figure we'll try them out and see if they will work for us. And we will also do tests of the tau adjust monopix chip from Bonn, which will arrive after Christmas sometime. So there's lots of exciting work going on. And that concludes this presentation. Thank you. Right. Okay. Cheers, guys. Oh, a blurry figure. Yeah, I just wanted to run through that, how it recorded. I need to make some changes, definitely. I go into a bit too much detail and such. Leave comments if you have any comments. This is weird. This is not a gaming video, but I wanted to record it, and I might as well put some physics on my channel as well, I suppose. So yeah. Talk is on Thursday. I need to work on it a bit. Not so much my rehearsal, but I need to change. Yeah. Oh well, I will discuss with my supervisors tomorrow. Boop, boop, boop. What else? Yeah, what else? That took 16 minutes, which is a bit too long. My talk is supposed to be 15, but maybe if I talk a little bit faster, it's fine. I mean, when I presented it to my friends yesterday, it was 15 dead on, so I think it's fine. If I make it a bit shorter, I can always waffle on about the SPADs a bit, because SPADs are very exciting. I hope to work with SPADs in the future, maybe. It's very neat. Anyway, I'm gonna stop talking now and go play some games instead. It's Saturday after all. Have some chocolate, play some games, talk to Tony. So yeah, I'll see you around, yeah? Sorry about this weird video. Bye.